Thank you all for joining. Feel free to ask questions at any time during the presentation. I'll refer to it from time to time and try to answer them and not try to put them all at the end. Today, we're going to be talking about FDM, toolpathing, and nTopology with a focus on infill. For a while, we've been tweeting pictures of things like these continuous toolpath, multiscale infills, and these stretched infills. And a lot of folks are asking how to do it. Now, it's a bit of an advanced skill, to be honest, in nTop. It's the ideal platform for doing this kind of work, but it involves a different way of thinking about infill. It involves thinking about infill as a solid model, which is not really solid, it's more of a surface. And so implicit modeling turns out is very powerful to work with that kind of shape, if you will. But it does require a little bit of elbow grease and a little bit of work. So in the past two webinars, I started to show some skills that it's good to have to build up to something. And here I thought I'd say, hey, let's not worry about all the little details, but let's try instead to give an overview of the process. And then if you want to do it yourself, you'll at least have a sort of a top-down map. So this is a bit of a different view, but we'll start by going right into the software and illustrating the basic concepts, which I like to call the zigs and the zags. So we'll have a basic shape like this, and I'll bring in a triangle wave to create a basic rectangular zigzag toolpath. Union these together, intersect these together. And we'll just go, let's say, diagonal with a period. And so here we've created some shapes back and forth to fill a box. This would be as if we're trying to make a box on our FDM printer. And these shapes are kind of like infill. The problem is that each one is an individual island. And when you're making FDM, you usually want to have a continuous toolpath. And so the zigzag technique lets you create a continuous toolpath out of two pairs of solids. So let's make some variables here. And we'll call this guy zigs. And we'll make a copy of them. And what I'll do is subtracting is just taking an intersect with a negative. And I prefer often just to put the negative right here when I want to flip the sign of something like this. Give it a different color. And so now we've created two models. We'll call them the zigs and the zags. And the key to making a toolpath is switching from the zigs to the zags magically in the right place. And that's an interesting question. What is magically the right place? But in this case, it's geometrically obvious. Let's just put it to work. So we'll slice. We'll start by slicing the zigs, let's say. Some reasonable parameters for a demo. Slice all the way down. And we need to chop it in half with something because we only want half zigs. And so we'll create a boundary. I'll just create a boundary the other way, diagonal. I'm cheating by making some not quite Euclidean distance fields, but in the sake of demoing, we'll hand wave at this a little bit later to show you the right way to do this kind of work. But we do want to split it there. And so that gives us a field, or the slices, for one half of it. And now we'll make the other half of it just by dragging the zags in. And we need to, should have made this a variable before. We want the negative there. And so here you can see we've made both halves of the toolpath from the zigs on one half and the zags on the other. And from here, you could use our merge slice stack command to make this one toolpath object. And if you here, and for the rest of the demo, we'll focus on solid walls because of their structural benefits. But if you wanted more of a crisscrossy infill where every layer did a different angle, you would just create more of these with multiple of the slice height you want and offsets, and then you can merge those together as well. So that's the basic approach. You make the zigs and the zags, and then you join them up in such a way that you get a continuous toolpath. Now let's zoom way out and take a look at a object of interest. So this is a part, it's based on a design that our friends at Stratasys have been doing in their advanced FDM product. There are a number of products, mostly from 3D printing vendors, that bring in precise CAD geometry and let you apply stuff to it. I think 3D Systems has one for metal called 3D Expert. And they're nice build setup environments. They all use the same paradigm. We're going to bring in a number of multi-body CAD file with a bunch of different regions, apply different properties to those regions, and then make a fancy part. And that's the main setup and workflow that almost everyone does in nTop as well. It's just with nTop, you can do all this crazy stuff to make it come out however you want. And so what you're looking at here is something that follows that approach, but for the infill, we use a similar technique, except we went to we have a honeycomb. You'll notice that the toolpath is the boundary between the colors. It zigs back and forth, zigs and zags back and forth. It welds to the bead. So as we do this, we need to maintain a constant weld, because assuming constant bead thickness, that's a manufacturing property, and it's multiscale. So how on earth did this come to be? Let's drive down until we can get to sort of the zigs and the zags layer of it. So the main block is one of the user-defined so-called compound blocks, which is this kind of multi-scale fill. So let's just go right to that block and see how it works. When I'm making my blocks, they usually output what they need to output, but I like to keep a few visualization techniques here on the inside, just so we can tell what's going on. And in this case, we're making our hexagonal fill. You'll notice that there's a degree of freedom that was not expressed in the part I just showed you, where we're varying the hexagons from being having a very small weld to increasing the size of the weld to where they become square and probably structurally quite different, all the way up to this auxetic, a very heavy but maybe mechanically interesting type of lattice that has these very large welds. So we are enabling not just multi-scale variation, but also different cells. And in particular, what's interesting is this modifier field that I've just got basically set to being distance to a point. If I hide the results, you can see there's the modifier field. There are a few different ways of doing multi-scale. This is one that I think is pretty quick and easy. It's limited in that it'll only work if you've got very smooth and slow transitions in your modifier field. If you introduce sharp transitions, it will give you discontinuities and a bad day. So this is one to be used with a little bit of care. But if I take a look at the field viewer, you can see that we've used the scale of the modifier to set a local bounding box size that's quantized to powers of 2 subdivisions, and then use that to create a field that will be the modifier to specify size. So that's the magic trick. It's doing it by sampling the 4 corners of each bounding box, which is a pretty poor excuse for the infimum or supremum functions that it's modeling. At some point, maybe we'll have something more like that that'll be a little more robust if you've got fast changing fields. But this works pretty well, and you can smooth them if you need to using smooth tools. So that's the basic approach. We just by choosing those subdivisions, everything else is standard modifiers. Or we'll look a little bit more into how we do the transition of the unit cells. So this one is built on a compound block that just knows how to do the infill without the multi-scale, because it's just applying that at the right, frankly, just multiplying the period by 2 and compensating the walls for each of the different subdivisions. So let's go down a layer lower into the one that just does the hex blocks. Oops, that's where we're going next. This one. Okay. So This is the non-multiscale version, and I use this one quite a bit because it doesn't have the sampling, and it's pretty fast. So we're varying wall thickness as we go along we're varying the cell size as we're going up. You can see that this is made out of a list of 4 objects, and I'll talk a little bit more about why we're passing a list around in a second. But this is basically adding these walls, which are both additive and subtractive here in Zigzag land, to something else, which are what I call just these hexagons. And that is, as we just revealed, the attached hexagon fill. And it's kind of interesting. If you look at the output of this, there are one of these sets of diamonds for the regular hexagonal side, and then the other is just a shifted set of diamonds, it turns out, for the auxetic side. And these are actually, these 2 offset sets of diamonds are just getting blended together. What are these made out of? Just to go all the way down, we could take a look at, we just start with a diagonal line. And this is why I was talking about the length compensation I hand waved over before. There you could take a look at a mirrored version of it. So we'll just reflect that on one axis. It looks something like that. And then the next step is to pattern it, and you get the fields that look like this once we've patterned it. So this is the low-level building block that we've then built a varying layer on top of, and then a wall, that's the thin-walled layer on top of, and then we built the multi-scale layer on top of, all while also being able to vary because it was set up from the output of this block. So let's go back and apply that to our little example. And I looked up and there aren't any questions yet. So here is our example. And let's replace this rectangular fill with the, we'll just use the varying hexagon fill. So here is the varying fill. And we'll also import a block called Consolidate Attached Hexagon List, which is a kind of chewy name. So when you are working with implicits that you want to warp, that stretching of the field is something that you need to stay in control of. And it turns out that the best way to do that is to keep a structure around of your objects and transform them and warp them individually and then put them together at the end. It's a little bit of extra complexity to manage on one side, but on the other hand, it actually gives you, well, a lot more power. And if you want to have multi-scale warped geometry while doing 5-axis conformal, you need to juggle all these different mathematical elements together. And I find it most convenient to do it in this order. There are probably other ways of doing it, but this is how I do it. So we'll bring in our fill itself, and that returns a list of 4 items. Make it a little bit smaller. Now, there's nothing really to see here yet when we apply it because we want these to be Boolean together in a certain way. And as you saw, we're blending from the hexagonal side to the auxetic side while adding and subtracting some walls. So there's this little decision tree of knowledge, or this Boolean tree that comes along with it. And that's how we'll apply it to a part. So we'll use this consolidate block, and we'll just take the output of our fancy underlying block into that because it knows how to deal with all the details. It knows how to manage a weld gap. It will give it 25% gluing. We won't worry about a blend radius right now on the edges. And we'll create this block, so 2 millimeters. And we can just replace our triangle wave up here with our new hexagons. And here they appear in the slice data as expected. Now, doing the slice on the diagonal is probably not the best way to slice them. Maybe we just want to slice that around the X direction, let's say. There. And so that shows how to apply it to the hexagonal fill at the basic level. Okay, so I think it's worth dwelling for just a second on why we needed to pass the list around. And in the webinar a little while ago, I showed some warping and gradients to get in control of it. But we were only doing that with one object at a time. So let's take a look at the application of it to just some basic ribs. And in the software, we provide some tools for remapping cylindrical that do this automatically. But it's nice to be able to look at what's going on. So under the hood here, we have a, there it goes, a square pattern that we wanted to turn into a polar pattern of ribs. And the normal thing to do is you can warp this into polar coordinates just fine, but everything gets stretched equally, including your ribs. And often in engineering, we want to make constant wall thickness ribs, and this is not that. So this is when we would be applying our gradient trick. If I take this finished Boolean result, I've been offsetting afterwards, but before the offsetting, divide by the norm of the gradient, it will do more or less what we want, but there's a gotcha. And the gotcha is because of all the stretching, the gradients are not really compatible with each other. And when you offset, you get these little kind of inclusions, at least with this geometric setup, right where these guys meet. And usually this is the opposite of what you want in a mechanical part. So this is from where we get the idea of always keeping a normalized field around, or normalizing as you go. If you're using maps that are analytic and well understood, like a cylindrical map, you can compensate for that analytically using the Jacobian of the map. And we have some blocks like the remap cylindrical body, which does that automatically, as opposed to the remap cylindrical field, which lets you stretch things because there are perfectly reasonable use cases for both. But that's what the difference between those is. And so if we looked at the final result here, when we do the where we normalize before we Boolean, everything comes out happy and as you want. But what it does mean is that our objects are these lists of fields and not individual fields as we transform and warp them around. And that's why you see in this FDM stack, passing a list around along with the helper function to consolidate them into a final body when we're ready. And with different kinds of unit cells, you might want to do that a little bit differently. By the way, if this seems all a little bit complex, it is. This is why I'm calling it advanced use of the software. And there are ongoing efforts at the company to package these things up in easier to use ways and make them more accessible. The reason for me going to all this depth with you right now is just to show you that you don't have to wait. You can do this today if you're willing to do the work. The platform's certainly capable of it. And we have customers doing this with great success. So that's how we make some of these different designs like this wheel where we're maintaining the welds perfectly. Actually, we can use our new measure feature to check out these welds. Forget what I told them they needed to be in this design, but you just zoom way in here and I think, look, okay, we drag it over there. So these are 0.5 millimeter welds, and you can see they're kind of nailed it down there. And then we can drag up here and we'll look at the welds up here and look at that. There's still 0.5 millimeter if you look down there. So clearly it works. Here's another kind of interesting example where we're modifying the unit cell as a function of radius, as well as we're packing them closer together logarithmically as we get on the inside there. And if you look at that and you've seen some math, you might say, hey, wait a minute, can I do that on an arbitrary complex plane using the zeros and poles to sort of remap to fields? And the answer is yeah. I'm not sure how practical it is doing mechanical design on the complex plane, because I find the fields and only having the poles and the zeros to warp around is kind of limiting, because you end up with these open saddle sort of spaces. But it's a pretty fast way to create some concentrated some concentrated cells in regions of interest like point loads. So that's the basic idea. And I'm about done. I'm going to show one more part. So now would be a really good time to ask questions if anyone dares. But to try to put it all together, I made this one part last night, and I confess I blew up my computer when I was doing the multiscale stuff. In the interest of getting things done, we'll add that back in later and upload the file. But I wanted to just show you that the beauty of working this way is that it works in 5-axis. It's everything I did, although it happened to be 2.5D as I was showing it to you, is just as well defined with vector fields and so forth in 3D. And so just by bringing in a CAD part, as one does, and would for, I think, any kind of modern print workflow, as well as some helper bodies to set up the U, V, W parameterization to map us into a 5-axis space, especially just using this mid-surface, right, to get a distance field from that, so we have accurate heights. And then trimming it back to the regular part creates these beautiful shapes. This is, of course, designed to be used with other solid bodies for the thick regions and so forth. This is just the infill object. And if all you do is use nTop to make an infill object and then bring it into an advanced slicer, that's fine with us, because I don't know any other way to make this infill, to be honest. And so here you go. In summary, with FDM, if you want to have a really sort of full fidelity deposition setup, you're going to want to be able to have multiscale. You're going to want to be able to warp, and you're going to want to be able to do 5-axis conformal. You want to preserve wall thickness and any critical welds, because those are a manufacturing condition. You want to produce continuous toolpaths so you don't have to lift the pencil. And you want complete control over your build directions and your process directions. And that is what I think I showed you today. So that's how you do it at a high level. If you want to do some of this yourself, feel free to reach out to us to get a little bit of hand holding as we set it up. If you want something a little bit different, there's plenty of room for tweaking. I hope this you can see this is just yet another point of departure. Okay, well, that's how it's done, everybody. Solid modeling using implicits for FDM. It's a pretty, I think it's something to aspire to in the software. I certainly was working at it for a while, because it builds on several skills: getting comfortable working with the math of fields and warping fields, the idea of delaying your Booleans to the end, and some multiscale latticing. So there you go, some things to work towards if you weren't, if you're staying at home for a few months and getting bored. This should keep you busy for a while. All right. Thank you all very much for attending. It's been a pleasure. Talk to you soon. Oh, wait, there's a question. It just popped up. Is the slice path directly applied to the FDM printing path, or could you pass in a CAD file to the FDM slicer? If this is a former case, could you please tell the G code is generated and passed to the FDM machine? You know, I should have answered that proactively. Thank you very much for asking. Okay. If you have a machine whose toolpaths we support, and for FDM, Stratasys is the big one. So they have a format called SSL, and that's a perfectly good way to do it, to go to their machines. The parts I showed you were made with the Raise 3D machine you can see behind me here. To do that, I actually just export STLs. I'll confess, lately I've been doing it in a CAD system. I'll go and I'll take my Zig and Zag CAD parts and just bring them both into a CAD system that I like, which is nTopology. Yes, I like nTopology. I also like Space Claim. So I find that to be a very useful system for this kind of work. And so I'll bring it in and just send the STLs to the printer. And then either in Cura or Simplify 3D, there's a control. Maybe I can quickly find it for you here. There's a control to adjust the offset in 2D. And so you want to make sure that you guys know what I've been doing. But if we look at the model here, there's a parameter. What is it called? Horizontal size compensation. It's called something different in Cura. But this you want to offset so you're printing right on the center line of the zigzag bodies, not inset inward or outward. And so I've mostly been doing it with STL and for consumer. Now, there may be some really exciting stuff in the not too distant future in that department. So if you are doing more there, we might have some things that you might to test or something like that. So reach out if you want to do some of this in the short term, and we'll talk about some of the works in progress to go to consumer FDM. If you want to use this kind of technique for metals, we have CLI and CLF and those kind of formats as well. Okay, thank you for asking that question. And thank you all once again for attending. I hope this was useful. I hope it gives you something to chew on. And I'll tell you, I mean, if it's not obvious, I've been pretty excited to kind of find this general purpose representation that I feel like is the right way for handling structural FDM parts. I look forward to seeing what you do with it. Bye for now.